Good afternoon. Wow, only about 30 people answered. There's about here, I would guess 320, something like this in here. Let's try again. Good afternoon. Okay, let's get air in these lungs and blood in the brain. So we're going to do here Chem 1A. I'm your professor, German name, Heino Nietzsche, okay? You used to have a governor who spoke South like me, but it's the only thing I have in common with him, hopefully. Okay, so all the information that you need is on BSpace, okay? Read it carefully, and read it again, and then you can write not me, but you write it to the address that I will provide to you in a couple of minutes. So there is we have split, we is not me, higher authorities have split Chem 1A in a lab section and then the lecture section. And it caused quite a bit of confusion, but we will make sure that this is all will be going smoothly. So you are here in the lecture section. Anything about lecture, you ask me, or the head TA. Anything about the lab, you direct to Dr. Daniel Kelly. Dan Kelly, he is right here. He is your person for the lab, he is the lecturer, and he also takes care of some of the issues that we have here in Chem 1A. If you have any question about enrollment, you contact Dr. Robert Lamoureux. Lamoureux, he is at 211 Latimer Hall. You go out the door, you know where the elevators are, this is Latimer Hall. You go to the second floor, 211 Latimer Hall. Don't talk to me, please, about enrollment. Of course you can talk to me, but I will send you to Robert Lamoureux, okay? I talk to everyone, okay? That's not a problem. That's the first thing. Let's talk to each other. That's very important. But let's also say something. That's even more important. Then we have Karen. No, she is the demo supervisor, Karen Chen. She should be here. And she's a demo, very important person, but I think she hates applause. So I always have a round of applause for her. She hates it, so that's why she's hiding, I think. And then we have the head TA, and the head TA, Emily. Emily is not here either. And Emily Chu is your head TA, and this is where you, anything about lecture, anything about discussion section, you write to chem1a.sp12@gmail.com. We will only read email that has in the header line your full name as you have registered, your student ID, and the words Chem 1A, or the word Chem 1A. If this is not in the headline, it goes right into delete, okay? So if you want us to respond, then we do this. And don't overwhelm her with mail. We have close to 1,000 students. That's a record. I usually have only 700, something like this. I don't know where the other 300 came from, but you're more than welcome. I love to teach you, okay? And so I have office hours today. So Chem 1A is difficult. For most of you, of course not. For some of you, it's difficult. And you need to work hard on it. And there are many possibilities to get help. One of them is the Student Learning Center. One of them, you come to my office hours. One of them, you come to the office hours of Dr. Kelly. And my office hours are Wednesday, which is the day from 5 to 6, and Friday from 3 to 4 at 446 Latimer Hall. Right out the door, up to the 4th floor, left of the elevator, left again, at the end of the hallway, left again. Okay, 446 Latimer. Starts today. Come and see me. We always have a lot of fun at office hours. Yeah, I really do. And Dr. Kelly's office hours are at 334 Latimer. You don't know where Latimer is. Mondays from 10 to 11 and Fridays from 10 to 11. And this is mainly for issues that deal with the lab. But he also will be able to answer some of the questions about lecture, if you're sort of mentioning on the side. We have weekly review sessions, and they start tomorrow. And I highly recommend that you go to these weekly review sessions. Tomorrow we're going to talk about, not we have specialists there who talk about this, about mastering chemistry and how to navigate, and we may even solve some of the problems with you. And the review sessions are held by Emily Chu, and they are Thursdays, every Thursday, except when we announce it doesn't happen, from 5 to 7 at 155 Twinnell Hall. That's close to Sproul Plaza. It's a huge lecture hall, 155 Twinnell Hall. Starts tomorrow at 5. Go there, highly recommend it. And get out of the starting hole now, today. Start today. Don't start just before the midterm or just before the final. It's too late. You won't be able to manage. Okay? And then you put even more stress on yourself that you already have. All right? Start now. Of course, we always have good intentions. Of course, I'm going to start now. But there's some great other stuff. And I have the other homework, and there's something on television. No, it's on the computer and all kinds of other activities. But I highly recommend it. And some of you are relatively fresh from high school. You already noticed it's a little bit different than high school here. Okay? It's pretty tough. And some of you were the best of the best, and you still are the best of the best. But look around you. They're all the best of the best. That's why they're in Berkeley. Okay? And we love you all and love to have you here. You have to also remember that somebody, usually the parents, they pay a lot of money for you to sit here. Okay? So it's a minimum of $7,000 or $7,500. If you're a foreign student or from out of state, it's like close to $13,000 if I recall right. And this is that's just for tuition. And that's supposed to be cheap. All right? So you use your time. Please use your time well. And I know that you all have the best of intention of doing this. And so there's the Student Learning Center. You can get help also. Or form some study groups. But really do study, not only drink tea or coffee, okay? Really be serious about this and get started today. I can say it often enough. Get started today. And many of you, especially some of the AP students, they're at risk because many of them think, or some of them, I think I know all this stuff, and then they don't pay attention, and so it went by them. And then they have to run behind it. So I don't know how this happened, okay? So get started today. Now, having said this, there's one more source of help. The Open Office, that's not a product that's on the web. The Open Office is at 106 Latimer Hall. In here, up one floor, out the back door to the right, you get to 106 Latimer Hall. There's, beginning on Monday next week from 10 to 3 p.m., 10 a.m. to 3 p.m., there's always a graduate student instructor, a teaching assistant there that you can ask questions. You just drop in there. Make use of it. Make use of it. It's very helpful. Extremely helpful. Okay, now what else do we have? iClicker. iClicker doesn't start until Monday. You get credit for being here, but you have to answer all the questions, and you will get the hang of it, how this all works. It also helps me verify and see that you have understood what I just told you. I will ask you a question concerning the material that I have discussed with you, and then you have 1.5 minutes, and you think about it on your own. That's the whole point. Don't talk to anybody. See if you can solve it, and then I see what the distribution is, and then I give you another explanation maybe, or some hints, and then you do it again, but you can discuss 1.5 minutes with each other. And then you try to solve it again, and hopefully you have it correct, or you went with majority. Sometimes the majority is correct. And this way you have sort of interactive learning, and you don't fall asleep also. And we give you some participation points. And this is all described in detail on BSpace, if you read it, please. Then now pull out your iClickers, please, and switch it on, and I have the following question for you. How many years of chemistry did you have in high school? 0, half a year, 1 year, or 2 or more years? Why don't you click in, and I see how many people are using the iClicker. It doesn't matter. We don't record today. We do record, but we don't count today. It starts this coming Monday. Homework is also due this coming Monday at 9 o'clock in the morning, 8:59 to be more correct. Or corrector. Okay? So, is everybody in? There got to be some more people here. We have only 248 iClickers. So you're responsible for the iClicker, that the battery works, that it works, and so on and so on. There's no way that I can retroactively help you with this. And so you're your iClicker, and you're responsible that it works. Okay? So 252, I think there's at least 400 people in this room here. So there's a lot of people who do not have any iClicker. Am I correct? Yeah, okay, good. Hope you have it by Monday. I posted it early enough. So let's stop this, and let's display it, and that gives me an idea what your dreams are. No, that doesn't give me an idea what your dreams are. Wrong question. I'm a question ahead of it. So there is 67%. Oh, so it's pretty good. 67% have 1 year. So there is a section at the beginning of the book. It has an F section or something at the beginning. And this is something you need to study on your own, okay? That will get you up to speed. Most of it, at least, you need to study on your own. Okay, so that's a pretty good distribution. Let's ask the next question. Now we're talking about dreams. Do you plan to go to medical school? A, absolutely. B, undecided. Or C, no. Let me open the polling. And let's see. How many were we? 242, wasn't it? 256? 252. Let's see if we reach it again. Or somebody already left. Okay, come on. Make up your decision. You can always change it. You can change it while you go along here. As long as it's open, you can change your answer. Okay? It counts the final answer. Is this your final answer? Okay, we lost 4, huh? Come on. All right, let's stop it. Let's display it. We don't want to waste much time. We're here to do chemistry, not to play games. But we do both, actually. That's a pretty good distribution. There is 68% who sort of wouldn't mind going to med school. Okay, that's a lot. And 30, it's always the same number, about 25 to 30% say absolutely not. Okay? And I wish you good luck with that. But this will be one of the first hurdles, or one of the hurdles you have to take. So, let's talk about chemistry. As I speak to you, there's chemistry going on in my body, in my brain. As I raise my hands, as I blink my eyes, as you listen to me, as you get bored, as you get excited, it's all chemistry. Chemistry is omnipresent, everywhere. The creation of the universe, at least for most people, it is chemistry. Okay? Some people doubt that, but that's a different story. And it's not part of this lecture here. So, chemistry is the science about atoms and molecules. Now, I have here some molecules, a large number of molecules of carbon. Let's see, I place this here, and okay, chemistry. Nothing happening. Boring. It's absolutely boring. I know there's chemistry. These are carbon atoms in this carbon sphere there. So that's not quite as interesting. So what makes it interesting is how these individual atoms and molecules react with each other. That's what we want to study. That's what we want to know. Of course, you need to know about the individual atoms themselves. But what makes it interesting, how they react with each other. And there are two ways to look at this. One way is the speed they react with each other, or the time it takes for them to react. That's called kinetics. And the other one is the change in energy before they reacted and after they reacted. That's called thermodynamics. And that's what we do here mostly in this class, thermodynamics. We will not talk about kinetics. A little bit today, though. Okay? Can you all hear me? Can you also understand me? Okay, good. All right. So we have hydrogen. Even those who never had chemistry, they heard about hydrogen. And those who never had chemistry, they heard about oxygen. Okay. So we have hydrogen and oxygen forms water. Hydrogen and oxygen forms water. Okay. So let's do that. And I need Karen now. I'm going to see where she is. Karen? It's at the beginning. It's a little rusty. Okay. Give her a hand, would you? There's Karen, the supervisor for all the demonstrations. So I have in this balloon hydrogen. What can you see first? In terms of density compared to our surrounding here. What's the surrounding? Mostly air, isn't it, right? Hopefully. And so it's lighter than air. It floats. Okay? So now I have hydrogen here and I need oxygen. Where would we have oxygen here? How much oxygen do we have in this room? Yeah, how much is it? How much? 78% oxygen. What else is in the air? Love is in the air. Never mind. So oxygen, what else was there? How much is there about? 78%? Okay. What else is in there? Carbon dioxide. That's a big issue. It's not a whole lot, but it's a big issue. When I was your age, it was 340 parts per million. It's now 370 parts per million. 370 parts per million. Constantly rising. By 2050, we expect about 450 parts per million. If you keep going like this, it looks like we're going to keep going like this. So that means the coral reefs will be gone, and a little bit water will be. Some of the people who live in Madagascar or something, they will have to grow some heights behind the Anyway, okay. So that's the CO2. That's called, what is it called? Carbon dioxide, and this causes what? The greenhouse effect, yeah? And this can cause global climate change. It used to be global warming, now it's global climate change, because it's pretty cold at the moment here, okay? And so we need hydrogen and oxygen. Let's do that here. So you notice nothing is happening. The hydrogen is there, and the oxygen outside. And if I leave this for a long time, that becomes flat, and then the hydrogen has diffused out and mixed with the air, but nothing happened. So let's investigate where nothing happened. So the timid among you, be careful. So I'm going to put that flame to the thing. Okay. That was a chemical reaction, wasn't it? All right. So the hydrogen was looking for the oxygen on the outside. So what this means, we had hydrogen and oxygen, and they had to have energy, certain energy. And let's say the energy is here. That's the hydrogen, that's the oxygen, and now they make water. Okay? And the energy goes down. Why do we know that the energy goes down? Heat, and you heard the sound. So there was energy given off. Okay? It was relatively long, the bang, wasn't it? Sort of drawn out. Why was that? Because each hydrogen atom had to find an oxygen, right? Each hydrogen molecule had to find an oxygen molecule to react, and this was just in the air here. So what could we do to make this a faster reaction? More hydrogen, yeah, but I only have that air here. More energy? No, the energy we need for something else, and I'll explain to you this to you in a minute. So what is that? So it doesn't have to look for the hydrogen. How would we do that? Put it in the balloon. Yeah, let's do that. So now it's going to be a little more noisy, but you still can stay in your seats. Let's see, now we have hydrogen and oxygen in the balloon. Let's see what happens. Careful. Good afternoon. Did you hear that? It was not as drawn out. It was shorter, because now the hydrogen did not have to search for the oxygen. It was right there. So there was a lot more energy released. No, it wasn't more energy released, because the amount of hydrogen is always the same we have in there. It was just released faster, because it didn't have to look. So if I integrate over the sound that you heard earlier, and integrate over the sound that you heard just now, it's the same area, okay? So what does this tell us? It tells us that it's a lot of fun chemistry, okay? So the first time we had it in the balloon, had to find the oxygen, and what happened, we had these reactants, we call hydrogen, and oxygen, we call them reactants, and this is a product, and there was a product. And what we followed, actually, was the reactants had energy, but they didn't react with each other. But then we reacted them with each other, we helped with that flame. And then we had the product, and this is an energy scale, and this is the reaction coordinate, or the time it takes for that reaction to happen. That would be kinetics. So the products you see here, the products, that's the energy scale, they're lower in energy, and this difference here is the energy that was released. So that's an exothermic reaction. It gives off energy. Exotherm, gives off heat. Exothermic reaction. And so why do we need that flame? That flame we need to get over the hump. Because it's called activation energy, and this is dealt with within kinetics. So we have to give a couple of molecules enough energy that they make water, and then that energy that's released is used for the other ones to get over the hump, okay? I could use a little flame here. That would be also fine. But that's how you get the reaction started. It has to overcome that energy barrier. Now let's assume we have a hydrogen leak. The tank is leaking, and I don't know that. And so there's the oxygen in the air, and it doesn't smell much, the hydrogen. And so the room fills, and we are sitting here, the room fills with hydrogen, and we have the oxygen. And then suddenly somebody comes and says, why don't you turn the light up a little bit? Boom! Okay? Because that light switch had a tiny little spark, okay? And the tiny little spark started the reaction, it released energy, and gave that energy for the others then to overcome that activation barrier, okay? So this is thermodynamics, that's the beginning energy state, that's the final energy state, and so this was exothermic, it released energy. We have other states where you have lower reactants and higher products, so we have to put in energy in order for this to run. But this is not what we talk about today. So you've also seen that there is a certain ratio maybe. So you see you have two hydrogens, and one oxygen makes two water. And this is molecules, or any other thing, but it's hydrogen, you need two of them, one oxygen molecule to make two water molecules. Now, we had in the balloon that was the second balloon, there was hydrogen and oxygen in a 1-to-1 ratio. How could we make it a little louder? We put double as much hydrogen as oxygen in there, okay? And the nice thing is that different gases in equal volumes have the same number of atoms or molecules. So you take the balloon, you know about what the size is, you put 1/3 of hydrogen in there, 2/3 of hydrogen, and then you fill the rest with oxygen, and this is what's hanging here. Okay, now I need to prepare you to close your eyes, not your eyes, your ears, and let's see if we get the windows to vibrate in the back there. Are we ready? Okay, is that true what I said? Okay, that was a lot bigger, wasn't it? So that's about as big. So now we had the right ratio, we had the right stoichiometry. That's all there is, that you have the right ratio. So you need 2 parts of hydrogen, 1 part of oxygen to make 2 parts of water. And if you have that right ratio, then the reaction goes complete. And that's called the stoichiometric reaction. Stoichiometry is nothing but ratios of reactants. And this is called a balanced equation. If I write hydrogen H2 and O2 here, and here 2 H2O, then it's not balanced. Okay? Because I need 4 hydrogens here, but I only would have 2 here, so I need to multiply this with 2. Then I have 4 hydrogens here, and 4 hydrogens here, and 2 oxygens. O2 is 2 oxygens. That's a balanced equation. All right, we can do this also. I can demonstrate this one more time to you. We have a little more fun. We do make exploding soap bubbles. Okay? Exploding soap bubbles. So what we do, we make soap bubbles with this little device here. We blow hydrogen in there, and then increasingly more oxygen. And you will see the difference, okay? Little tiny bubbles. You will see what they do. And I need to watch them not to blow up Karen by accidentally. Okay. Oh, nothing, huh? Just hydrogen. Okay, let's go. Aha, we increased the amount of oxygen. There it is. Aha, we have to reach the stoichiometric equation. Or stoichiometric ratio. That was not the... Whoa, okay, enough now. That's it. Thank you, Karen, and thank you. All right. That's stoichiometry, a balanced chemical equation, okay? Now, you see here, there is this activation energy. That's the transition state we have to overcome. You only need a couple of atoms to do that. That gives the energy to rest, and then it's like a chain reaction, and it happens. So if I use a tiny little spark on this, if it penetrates the balloon, then it would work. So that's what I did then. Okay, so now it's easy to do chemistry with gases because equal volumes of different gases have the same number of atoms. And you see, I showed you this on a molecular basis. 2 hydrogen atoms, 1 oxygen atom gives 2 water atoms, right? So how would you, if it's not a gas, how would you figure out